Learning-based event reconstruction for shallow in-ice ultra-high energy neutrino detectors. It's a mouthful to say, but more information can be found in this archive link down here. So we want to do event reconstruction of in-ice measurements using the radio technique for a shallow detector station layout. And this was then first used in Ariana, but it's also now part of RNOG and also IceCube Gen 2. We want to reconstruct the direction, the shower energy, and the flavor for ultra-high energy neutrinos. And this is actually the first work that is able to extract the flavor from in-ice radio detector data. Traditional methods, they have shown promising results for shower station, but there has not yet been a full end-to-end reconstruction so far. And it's very difficult to reconstruct this information by hand, as you have seen earlier today, and developing algorithms is quite time-consuming. So we want to use the deep learning method instead. So here to the left is an advanced example. So as you've seen the station layout here today, we have 4 LPDA antennas here, and then 1 dipole antenna as well. So 5 antennas in total. And you can see a high signal-to-noise ratio event here. They are very rare, but you can see that you have a direct and a reflected pulse, and the pulses are very short in time scale, roughly 10 to 20 nanoseconds. But most often you see these low signal-to-noise ratio events, which are much more common. So we want to extract the direction, the flavor, and the energy just by this data, nothing else, no interaction vertex or anything else. We use the ice profile of the south pole, and we use the same trigger that IceCube Gen 2 is going to be using, planning is going to be used, which is like a bandwidth optimized trigger. We use no quality cuts, so we use all the triggered events for this. Right. So I won't be covering this too much because we already went through it today, but basically we use 2 different Ascarian models, this frequency domain parameterization, which is Alvarez 2009. I will be labeling it that, and also this semi-analytical calculation with this shower library, which I will call ERC 2020. We generate roughly 20 million events using new radio MC, which we're also being covered today, with neutrino energies in the energy interval of 10 to the power 17 to 10 to the power 19 electron volts. And the shower, of course, if you look at the different interactions that you can have a short current interaction and neutral current interactions. So you can have electromagnetic components from these electrons here. You can also have hadronic components just from this hadronic shower. So we basically construct these 3 different data sets. The last one also containing then the electromagnetic shower component, which has previously been proven to be very difficult to reconstruct. You can see here the distribution of the events that we generate as a function of shower energy for the 3 different data sets. So one thing that you have to take into consideration when using traditional techniques is that showers that also contain electromagnetic showers are affected by the LPM effect. So basically this causes some stochastic fluctuations of this charge axis. So we can see here 2 events to the left. You have an event, so on the y-axis is the short axis, and then the x-axis is the shower length. And what you can see for this 10 to the power 16 electron volt event is that we have 6 realizations of this charge axis, and they look basically the same. And also the electric field, as a function of time, look basically the same for these 6 realizations of the same event. But what if you go to 10 to the power 19 electron volts, so quite a bit higher, you see these 6 realizations basically look very stochastic, and this is what makes the electromagnetic showers so difficult to reconstruct. And you can also see the electric field being very different for all of these 6 realizations. But this is also quite interesting because this gives us flavor reconstruction sensitivity, so that's quite good later on in the topic. So, of course, as someone stated, we have a deep learning model, so we need to present the model here. We use an input layer, which is, again, remember the 5 antenna traces with 512 time points is what we use. So that's what we input into this model. And then we also have these convolutional blocks here, which have convolutional layers and some pooling, yada yada. You have some filters in these layers which go down with the amount of layers, amount of blocks that we use. and some batch normalization and flattening, and I know these are just weird words. But then you have these dense layers here, which also like decrease in units until we come to the end. And basically, in the end, we have this output layer here, which is basically the direction or the energy or the flavor of. So basically, that's what you get from this model. It spits out the thing you want, basically. So now we train this giant network of millions of parameters, and we want to reconstruct the direction. So this is then the results from that. So what you see here are the 3 different data sets I talked about earlier, and you can see the space angle difference histograms here. So what we see from these results is that you get a Gaussian part, basically, with an extended tail. So the Gaussian part of these are quite narrow, so roughly you see 0.5 degrees to 0.8 degrees for this more complicated data set. Basically, the complicated data set is a bit worse, but it's still performing quite well. And this extended tail here makes it such that the 68% quantile is quite a bit larger. So the 68% quantile is roughly 4 degrees or 5 degrees, depending on the data set. So it's quite interesting that we also get like a degree angular resolution for these complicated events, which in previous analysis have found either they ignore them or they found that it deteriorated the reconstruction performance significantly. So this is very exciting. Yeah, you can also look at these angular resolution as a function of true neutrino energy and also event signal to noise ratio. And we can see that it improves with both energy and signal to noise ratio. And the causes of this is likely that you have fewer events at low energies, as we said in these distributions. So we have fewer events, and the network hasn't seen as many low energy events, and then hence it's worse at reconstructing low energy events. And also for the signal to noise ratio, it makes sense that high signal to noise ratio events are reconstructed better because you have less pattern compared to the signal. And we think that there's more potential here at a low energy event, low energy regime, if we just improve and increase the amount of events at these energies. So then we can also look at the results for energy. What we see in these plots are the logarithmic energy differences between the true and predicted energy, and for the 3 different data sets again. And we can see that we can reconstruct the energy within a factor of 0.3 roughly in logarithmic space, in log 10. So this is a factor of 2 in linear space. And this matches then to this fulfills the science requirements because this matches the irreducible uncertainties from inelasticity fluctuations, which also we covered earlier today. So we see that this complicated event class is still being reconstructed quite well, similar to the others. And it's more interesting to look at these heat maps, where you can see that on the y-axis it's the predicted energy, and the x-axis it's the true energy. And you can see that for low true energies, we are predicting a bit too high of an energy. That's why there's this skewed kind of tail here. And this means that we have a good correlation for most regions, but not like at lower energies, it's not working quite as well. And the cause of this might be that we have these fewer events at lower energies. So again, we think we can improve this by just increasing the amount of events. Right. As for flavor, this is, as I said earlier, one of the first results that we can actually reconstruct the flavor from these kinds of measurements. So what we can do is that we can reconstruct neutrino, electron neutrino charge current events from the rest. So there are basically 2 classes that we can distinguish between. And as a reminder, if an electron neutrino comes in and interacts with a charge current interaction, it produces a lepton, and that lepton would be an electron in that case. And that's one class, and then the rest, all the neutral current interactions, and they are part of another class. So the results are here. This is for a certain energy interval, as you can see here. And on the y-axis, it's the true label, the actual true class. And on the x-axis, it's the predicted label, which the network then predicts. And how you read this, it's called a confusion matrix, and it's supposed to make you confused. But you actually read the diagonal, and that means if there's a large number in the diagonal, it's a good thing, because that means you're predicting the correct class. And if you read the off-diagonal terms, they mean, okay, so 23% of the new ECC events, for example, are predicted as the rest. So that's 23% of the cases that are predicted as wrong. And in this case, 10% of the rest are predicted as new ECC. So, but you see we get a 90% correct for the rest, and the 77% correct for new ECC. Also, we can look at how this then changes with energy. So this is just increasing energy bins, and we can see that it improves with energy. We see that first we get quite bad. Again, look at the diagonal. We get quite bad at low energies, but still some sensitivity. But then once we go up in energy, we get much better performance. And this is something that we quite expect, because the LPM effect is more prominent at large energies. So it's a lot easier to distinguish the flavors, because these events are more affected by LPM. Right. So for the outlook, we want to do some sort of uncertainty estimation, because so far we have only predicted the nominal values, and we haven't predicted the uncertainties. So we want, often we want the uncertainties because they're often as important as the nominal values. We're physicists, so we want this. So what we also need to take in consideration is that it's super important with these uncertainties, because the direction uncertainties are like highly non-Gaussian. You know, we've seen these banana shapes in the sky today also, and it's also very difficult to do using traditional deep learning techniques. So instead, we could do something called normalizing flows, which is again one of these buzzwords in neural networks, and you can predict event by event uncertainties using this. So this then, instead of predicting the nominal value, like the energy or the direction, it predicts the probability density function instead, which is very cool. So to the right here, we have an example. So the blue line, this is just a plot of the energy on the x-axis. So the blue line is the true energy of this event, and the black distribution is a probability distribution that the network has produced. So the network thinks that, okay, I have this distribution here from this event, and then we can read some sort of error, like the width of this distribution, for example. That could be one way of getting the error. So basically, you also get the error in these nominal values as well, and not just the nominal values. One thing we also want to do is end-to-end detector optimization. So, as we talked about earlier today, now is a great time to improve the IceCube Gen 2 designs, the station layouts. And this is not possible right now because the Monte Carlo simulations are very time-consuming, and developing like these reconstructions takes super long time. But we can use neural networks, and we can replace like the entire pipeline that we have with fast and differential surrogate models. So this then tackles two most time-critical parts of this: the generation of the stereo signal and the ray tracing. So we use GANs for this, generative adversarial networks, and these can then generate events based on some conditions like the energy and the viewing angle from the Schreiner curve. And we train this, for example, on ARC 2020 data. So on this plot to the right, we see an example. We see on the x-axis it's just the time, on the y-axis it's an amplitude, and on the blue striped lines and the orange solid lines, that are two different just amplitudes at two different viewing angles. And what we see here is that we can generate these gray lines here using this generative adversarial network based on these conditions of the energy and the viewing angle. So we can generate these stochastic events that we might use for then propagating into the ice. Right. So as a summary for this, we see that deep neural networks work really well for reconstructing neutrino properties. At least they show great potential, we think. For a shallow radio station, we get the direction with a theta Gaussian. This is like a Gaussian part of 0.6 degrees, 68% quantile of roughly 4 degrees, at least for the hadronic events. For the hadronic and electromagnetic events, it's a bit less performance, but still within quite good regions. Also, we get the energy within a factor of 2, roughly, and the flavor within, quite good, 70% accuracy for these events and 90% accuracy for these events for this energy interval. And this is using all triggered events and no quality cuts. And again, we only use the signal traces, no other information about the interaction vertex or interaction distance or anything else. So we don't even know the station layout. We use the data. The data was generated using UREG-MC, so that's where you put the station layout. So we use a similar model for all of these properties, which shows that DNNs generalize greatly to many different tasks. And that's quite interesting as well. So as for the outlook, we want to do event-by-event uncertainty prediction using normalizing flows. We want to do end-to-end detector optimization with fast surrogate models. And we also want to apply this to deep detector station layouts. Thanks a lot.